There are special graphs in the literature that you may come across when you start working on a specific problem in some application domain. The special graphs that we come across in the literature are, I write along with the notation Pn, which means it is path graphs. So path on n vertices looks like this. Vertex number 1, vertex number 2, vertex number n minus 1, vertex number n. So path graph on n vertices has got n vertices and n minus 1 edges. Then there is something called Cn, it is cycle graphs. Say V1, V2, V3, V4, and this side if you see, let me say Vn and Vn minus 1. Now if you join the first vertex and the last vertex in a path, what you get is a cycle. This has got n vertices and n edges. Then there is something called trees. So trees are acyclic and connected graphs. So it satisfies two properties. One is acyclicity and another one is connectedness. Acyclic graph has no cycle in it. Connectedness, for all u comma v in G, there exists a path connecting uv. Fine. If you look at this graph, this has cycle in it, so this is not a tree. If you look at this graph, all of this form G. Now each of them is acyclic, but if you take this as U and this as V, they don't have a path. So this one is not a tree as G is disconnected. So which means possible examples are, they look like this. So this is an example of a tree, and this is an example of a tree. So as you can see that if you take this as U and this as V, there exists a path connecting UV. And if you take this as W and this as Z, there exists a path connecting this. So we come across trees in the context of database systems. We come across trees in designing computer networks. We talk about spanning trees. We talk about weighted trees. We talk about something called weight of a minimum spanning tree, and so on. So apart from this, we also come across two other graphs, namely bipartite graphs and planar graphs, which we shall see next. What are bipartite graphs? As the name suggests, bipartite, so bipartition, bi means two, so there are two partition. G is bipartite if G can be partitioned into two sets, V1 and V2, such that for all u comma v in the edge set, u belongs to V1 and v belongs to V2. So G is bipartite if G can be partitioned into two sets such that if you look at an edge UV, then one endpoint is in V1 and another endpoint is in V2. This is true for all edges, which means there are no edges inside V1, there are no edges inside V2. So what this says is, suppose graph looks like this. So to say that this G is bipartite, we need to exhibit two partitions of G, namely V1 and V2, with the property that now it's a partition, so which means A to F is distributed into V1 and V2. And what is the definition of partition? V of G is union of these two, and V1 intersection V2 is empty. Okay. Now let me place A and then C and E, then B and then D followed by F. Now if you take the union, you get V of G, and intersection is empty, and A appears only here but not here. Similarly, F appears here but not here. Then the edge constraint is, you choose any edge, say BC, you see that it is from V1 to V2, or one endpoint is in this partition, the other endpoint is in this partition. Look at AB, AB is like this, and CD is like this, DE is like this, EF is like this, then AF is like this. So it tells you the following: V1 is an independent set, V2 is an independent set, and edges are from V1 to V2. So look at this graph. What are these graphs? They are trees. Just now we have seen trees are acyclic and connected. Now what I do, let me label this one as A1, A2, A3, A4. What I do, I place A1 here and A2, A3, A4 here, which means the first level appears like this. Then A5, A6, A7, A8, I will place it here. A5, A6, A7, A8. A2 is adjacent to A5, A3 is adjacent to A6, A4 is adjacent to A7, A8. Then you have A9. A9 I will place it here, and A5 is adjacent to A9. Then A10, A10 I will place it here. As you can see, if you alternate between V1 and V2, meaning vertices at level 0, 2 and 4, they are placed in one partition. Vertices at level L1 and L3, they are placed in other partition. So if you alternate between V1 and V2, you see that in fact all trees are bipartite. Okay, so trees are special case of bipartite graphs, wherein it ensures connectedness as well as acyclicity. But in general, bipartite graphs can allow cycles. Now the interesting question is, can it allow any cycle? In this case we saw that it is a cycle of length 6. Now say cycle of length 5 or 7, does there exist a bipartition? The question is C5 or C7, cycle of length 5 or 7, is it a bipartite graph? So let's ponder on that next. Consider a cycle on, say, 5 vertices A1, A2, A3, A4, A5. Now let me try exhibiting a bipartition for this. So let me place A1 here and its neighbors A2 and A5, because these two have to be independent set. Then for A2 let me place A3, and the next one, where do we place A4? Supposing I place A4 here, then what will happen? A4 and A5 are adjacent, then this is not a bipartite. So if you try placing it here, then A1, A3, A4, A2, A5, then you see that A3 and A4 are adjacent. So that shows that this one does not have a bipartition. Intuitively, you look at two partitions, V1 and V2, and we know that this is an independent set and this is an independent set. So cycle starts from some vertex, then alternate between V1 and V2, and then come back to this. You choose some vertex. Let me choose this vertex. So we go here and then come over here, go here. So like this we alternate. And when you know the cycle completes, you come back to this. So if you count, it's always an even number. 1, 2, 3, 4, 5, 6. So now, because you alternate between V1 and V2, if at all there is a cycle, then it has to be an even cycle. So no odd cycle can exist in a bipartite graph. It's a powerful observation. In fact, it becomes a characterization as well. A graph G is bipartite if and only if it's necessary and sufficient. If and only if G has no odd cycles. Odd cycles meaning a cycle of length odd. So we said Cn, but if you write C2n plus 1, that will capture odd cycles. G has no odd cycles. So if at all there is a cycle, then it is only an even cycle. Which means if G is bipartite, 1, it is acyclic, which means it is either a tree. If it is connected, it is trees. If it is not connected, then it is forest. And otherwise, it has only even cycles. No odd cycles. So bipartite graph, again we come across in the design of computer networks and in the design of circuits board and in scheduling problems in operating system, many scheduling problems in the context of cloud computing, operating system, distributed computing, they all can be modeled as appropriate problem in the context of bipartite graphs. The next one is planar graphs. A graph with a plane drawing. So plane drawing is a drawing in which no edges cross each other. Let's look at this graph. It is a complete graph on 4 vertices, or it is also known as clique of size 4. It is a complete graph because all possible edges are there. So complete graph on 4 vertices, or it is a clique on 4 vertices. So complete graphs have maximum number of edges. So if you look at Kn, so Kn has got maximum number of edges, which means n into n minus 2 edges. Now the question is this graph planar? Is K4 planar? So to talk about planarity, you have to exhibit the underlying plane drawing. Just by looking at, one cannot conclude, because this drawing is not a plane drawing, because no edges cross each other. Here you see that these two edges cross each other. So can I redraw this graph? For example, let me redraw this edge. I'll take it outside and then draw it like this. Because when we draw, we don't talk about length of the edges and this is how it has to be drawn. So no restriction on that. So one can always redraw the edges so that no edges cross each other. You look at computer architecture design. For example, any printed circuit board design, no two electrical wires cross each other, which means the underlying graph for a computer architecture or any circuit design is an example plane graph. So now you see that this is a plane drawing, therefore K4 is a planar graph. Now what about K5? So this is K5, complete graph on 5 vertices. When we try redrawing this, I have to redraw in such a way that no two edges cross each other. So this one I'll draw like this. The edge from this to this I'll draw like this. Now we need to draw an edge from here to this, but that will either touch this, or if you come like this it will touch this, and if you try redrawing that edge it will cross some other edge. So no plane drawing exists for K5, no plane drawing exists for K5. This implies that K5 is non-planar. But interestingly, you just drop one edge, because we had difficulty in drawing the last edge, right? Except that edge, every other edge we were able to draw, correct? So interestingly, K5 minus E, when I say E, remove any one edge. Remove any one edge. Interestingly, K5 minus E is planar. You just remove any one edge from K5, that graph we denote it as K5 minus E. K5 minus E is planar. So there are many interesting graphs that we come across in the literature. Some of them are planar, some of them are non-planar, and it is natural to ask, is there a necessary and sufficient condition to comment on planarity? So as far as bipartite graphs are concerned, we see that, say look at K2, 3, we denote this one as K2, 3 because it is a complete bipartite graph. Okay, so let me draw like this. So these two, what we will do, we can draw one edge like this and another edge like this. So K2, 3 is planar. So it is a complete bipartite graph with one partition is having 2 vertices and another partition is having 3 vertices. Now the interesting question is what about K3, 3? Is it planar? And what about K3, 4? What about K3, 3 minus some edge minus E? Is it planar? All that we shall see next. Let's check K3, 3. So let me draw 3 vertices over here and another 3 over here. So the first set of edges we will try drawing without crossing. This comes over here, this comes over here, and this we have drawn, and this we have drawn. Now you see that we need to draw one more edge from this to this, which is not possible. When we try drawing from this to this via this, then we need to cross this. If you go like this also, it's the same thing. So which means K3, 3 minus E is planar, while K3, 3 is non-planar. I've given one sample drawing. You can always try redrawing it. However way you do it, you see that K3, 3 is non-planar, whereas K3, 3 minus E is planar.